You may be wondering why I sent you the materials for Module 14 before we did Modules 12 and 13, and there's actually a couple of different reasons for that. One of those reasons is because I know that some of my students are choosing to take the AP exam, and while I don't necessarily recommend that, for those of you that are planning to take it, I want to do Module 14 first because Modules 12 and 13 are both about organic chemistry, and there is no organic chemistry on the AP. There is a little bit of nuclear chemistry on the AP just as far as reaction kinetics. So that's why we're doing Module 14 before we do 12 and 13. The second reason is that I kind of like the flow of material a little bit better, simply because we talked about reaction kinetics in Module 11, and then in nuclear chemistry, these are all first order reactions. And so some of the things that you've already learned about half-life and things like that are going to apply very well now when we study nuclear chemistry. So that's the reason why we're doing these modules out of order. In first year chemistry, we discussed the structure of the atom. In fact, you probably talked about the structure of the atom way before you ever even got to chemistry. You learned that the protons and the neutrons are in the nucleus, the electrons are in orbits that surround the nucleus. And in first year chemistry, we touched just very briefly on how all of the protons could be pushed together so tightly, even though the charges should repel each other because they're all like charges. We mentioned that there was a very, very strong force that holds those protons together so that the nucleus doesn't just fly apart. And so now we're going to go into a little bit more detail about that. Most of us have probably at some point have seen Einstein's famous E equals mc squared. And while that equation can be used for lots of different applications, in this particular application, what happens is that the nucleons, which is just another name for protons and neutrons, the nucleons actually give up a little bit of mass in order to be in the nucleus. And then that mass, part of it goes to make pions, and you're actually going to read about this in the next section, so I am jumping the gun just a little bit. Part of that mass goes to making pions, and those pions are actually exchanged back and forth between the nucleons. Way I kind of like to think about it is if you've got a group of kids and they're standing around and if there's 3 kids, maybe they've got 3 tennis balls and they're just constantly throwing them back and forth to each other, just kind of keeping those tennis balls in constant movement. Well, that's kind of, in a sense, what the protons and the neutrons are doing with these pions. So each proton and neutron gives up a little bit of mass. The mass goes into making the pions, and then the pions are exchanged among the nucleons. And part of the mass that they have given up also goes into allowing for kinetic energy of the pions. And so the nucleus is actually a place full of all kinds of activity. It's not just all of the protons and the neutrons kind of sitting there in a lump. They're continually exchanging pions. Pions are very, very short-lived. So when a proton or a neutron catches a pion, it will absorb it, and then it will have to re-emit another pion. So lots of things are going on inside of the nucleus. We can actually calculate the amount of energy, including the pions, that is holding a nucleus together by using this. And the amount of energy that the nucleons give up is called either the mass deficit, or in some textbooks, you'll see it called the mass defect. Okay, so both of those are 2 terms that mean exactly the same thing. That mass is then converted into the binding energy. And the binding energy is the amount of energy that holds the nucleons together. Or you could also think of it as the amount of energy that would be required to pull them apart. Now, if I graph the binding energy for an atomic nucleus versus the mass number, what you will see is that the amount of binding energy is the highest up here at this point for an iron 56 atom. So what that means is that this one is the most difficult atom in creation to be able to pull its nucleus apart, to pull its its protons and its nucleons, or protons and neutrons apart, to be able to pull those, to separate them from one another, okay? So basically anything else, as we continue throughout the chapter, I want you to kind of keep this in mind, because a lot of nuclear reactions and other types of radioactive decay, that as we go through the chapter and talk about these things, we'll see that this is kind of the end goal for all the other nucleons. This is the most stable place to be. So just like when we talked in first year chemistry about how everybody wants their electron configuration to look like a noble gas, because that's what is most stable for them, is if the outer shell of electrons is full and it looks like that of a noble gas. As far as the nucleus is concerned, this is the most stable place to be, and so everybody wants to look like that, okay? Now, that doesn't mean that everything in creation turns into iron 56. If it did, we have a problem, but our creator's smarter than that, so we don't have to worry about that. Let's do an example so you can see how we actually calculate this binding energy. So we're going to look at example 14.1, and I have already put all of the relevant information that we're going to need up here on the board: the mass of the proton, the mass of the neutron, the speed of light, which is what C is in this equation. Energy equals mass times the speed of light squared. And then the conversion factor between AMUs and kilograms. So we are given the mass of a lithium-7 nucleus to be 7.0160 AMUs, and we're asked to calculate the binding energy. Well, in order to calculate the binding energy, I first have to calculate the mass defect. So in order to calculate the mass defect, when I look at this, now hopefully you will recall that when I have a symbol like this, what this really means is, if you look at the periodic table, you can see that for lithium, the atomic number is 3. And so that means it's going to have 3 protons in the nucleus. And I could write this down there if I wanted to. So this is the atomic number. This is the atomic mass. So in lithium, I have 3 protons. And then as far as neutrons, in this particular isotope of lithium, I have 7 minus 3, or 4 neutrons. So if I want to calculate the mass of what this lithium atom should have, according to the particles that make it up, I'm going to have 3 protons, and I'm just going to write a little proton down here so that you remember that. So the 3 protons should each have a mass of 1.0073 AMUs. And the neutrons, then, there are 4 of them, and they should each have a mass of 1.0087 AMUs. Okay, so if I had all of the protons and the neutrons kind of set out in particular by themselves, and then I just weighed them as to what the total should be, I should come up with 7.0567 AMUs. But as we've already talked about, each one of those protons and neutrons gives up a little bit of mass so that it will have the binding energy needed to hold together in the nucleus. So now I'm going to take this number, is 7.0567 AMUs, and I'm going to subtract the amount of mass that this nucleus actually has. So 7.0160 AMUs. And then when I subtract that, I'm going to end up with 0.0407 AMUs. So this is the amount of mass that has been converted to energy in order to hold this nucleus together, okay? Now, when I calculate energy, I calculate it in terms of joules, and you should have already taken physics. So a joule is a kilogram meter squared per second squared. So I need to change this AMU to kilograms so that it will work in this equation over here. All right. So this is just going to be a real simple mass conversion. So I'm going to take my mass that I'm trying to convert and put it over 1. And then I'm going to take this conversion factor. I'm going to put AMUs on the bottom so that it will cancel. And I'm going to put 1.6605 times 10 to the negative 27th kilograms on the top. So this cancels out. And that's going to give me 6.76 times 10 to the minus 29th kilograms, okay? Now I have this in units where I can utilize my E equals mc squared. So if E equals mc squared, I'm going to take the mass that I just calculated, 29th kilograms, times the speed of light squared, which is 3.00 times 10 to the 8th meters per second. And I will square that. And then the final answer there comes up to be 6.08 times 10 to the minus 12 joules. Okay, so that is the binding energy for that nucleus. Now, he goes a little bit further after he finds the answer to try to illustrate just exactly how big that is. This is the binding energy. That's the final answer. But what he's doing is he's going to tell you, well, how much energy does that actually relate to as far as something that I understand? 1 joule is approximately the amount of energy it takes for you to lift an apple to your mouth, from the tabletop to your mouth. Okay, approximately. If I have a mole of lithium atoms, we know that a mole is approximately going to be 7 grams. You have just 7 grams of lithium atoms, and you take this number and you multiply it by 6.02 times 10 to the 23rd, which is Avogadro's number for how many atoms are in a mole, you end up with the number that he gives you there at the bottom, that 3.66 times 10 to the 12th joules per mole. And what he's saying is if you have just 7 grams of lithium, which is not very much, that is the amount of energy holding those nuclei together in that 7 grams of lithium is equivalent to 1 3/4 million sticks of dynamite. So there is a tremendous amount of energy held together in the nucleus of the atoms. And that is why when we get to the end of the chapter, you'll see that you can have so much energy released when we talk about nuclear reactors or atomic bombs or something in those areas of chemistry as well, okay? So you're going to have several different problems to do where you're going to be calculating this binding energy and kind of going back and forth and figuring those types of things out.